second part of the afternoon session, I should say. And we have 3 more talks to go. We will start off with Dr. Quy Sun. He's with Südchemie Inc. in Louisville, and his presentation will focus on insights into the nature of the performance of nickel-based catalysts for diesel cleaning. Please.
Thank you very much, Oshi.
Actually, that will not work. You're blocking it. Leave, please leave.
Good afternoon. It's my pleasure to have this opportunity to talk about recent research result in Südchemie about fuel cleaning. The topic I would like to bring to you the insight into the nature of the performance of nickel catalyst for diesel cleaning. And fuel cleaning is very important and very urgent because the dirty fuel will seriously impact the environment and health of human being. So the dirty means 2 things. One is the sulfur and the nitrogen, and the second is the aromatic. So the clean fuel means the deeply desulfurized and the deeply dearomatized fuel. New environmental regulation requires 7 to 15 ppm part per million sulfur in ultra-low sulfur diesel and aromatic free. Actually, mostly people only concern about the sulfur and the nitrogen more than aromatic, but aromatic has very bad impact on the environment and health of the human being. For example, there is a very fine particle. It is called diesel soot. It's a kind of microparticle suspended in the air, and it directly harms our health. The production of this diesel soot directly related to this aromatic. So normally, if we talk about the fuel cleaning, we mean the removal of we need to remove both sulfur, nitrogen, and aromatic. Currently, the sulfur and aromatic removal include 2 technologies. One is the high temperature, high pressure, and low space velocity hydrotreating on this bimetallic catalyst. And another technology is a 2-stage process. The first stage is the hydrotreating to remove heteroacrylic sulfur compound, and followed by the catalytic removal of aromatic and tough sulfur species. For the catalyst, normally we can use the noble metal catalyst, or either we can use the nickel-based catalyst. These catalysts have their advantage and disadvantage. For example, for the spot noble catalyst has excellent hydrogenation activity, but sulfur it is very sensitive to sulfur, especially at a low temperature. Also, noble metal catalyst is very expensive. For nickel-based catalyst, it has a bifunction. Both can remove aromatic by hydrogenation and desulfurization. However, with the deposition of the sulfur or this nickel catalyst, this catalyst will gradually deactivate. So to improve the durability of the nickel catalyst will be a challenge. There are normally in refinery, aromatic hydrogenation removal always is accompanied by the sulfur removal. There are many different kind of sulfur species in the fuel, and their reactivity for cracking and hydrogenation are very different. For example, siphon is very easy to be hydrogenated and all cracked, and it is very easy to be removed. Compared with the diphone, this compound is very tough, very difficult to be cracked or hydrogenated. Such a chemistry will be involved in the fuel cleaning. For aromatic removal, it's very relatively easier. aromatic can be hydrogenated to become a reduced hydrocarbon, and it can be taking place at a low temperature. But for sulfur removal, it is pretty complicated because there are two groups of sulfur species. I call it the soft sulfur and the tough sulfur. Soft sulfur includes some sulfide or diaphones. It can be very easily hydrogenated to become H2S. H2S can be scrubbed by sodium hydroxide solution. If the opposite reaction at a low temperature, this is H2S might stay on the catalyst and poison the catalyst. However, mostly this sulfur species already is removed in the first step. So only this very tough sulfur species is retained in the fuel for deep cleaning. This tough sulfur species can be removed by cracking reaction followed by hydrogenation, also direct hydrogenation. Because it is tough, sometimes this reaction will be very difficult to take place. So we also can use the direct absorption of these sulfur species on the catalyst. The existence of the sulfur significantly impact the catalytic performance. For example, it may poison the active site and lower the hydrogenation activity, shorten lifetime of the catalyst. As a result, it will the aromatic and the sulfur species will lead to the fuel and the lower quality of the fuel. So many people have been trying to overcome these difficulties. For example, they try to improve different processes or develop different catalysts. Also, some people try to develop new technology. For example, develop a high-performance selective adsorbent for aromatic and sulfur. Also, some people try to think about biocatalysis technology. So the Kimi has a long-term program for fuel cleaning. They developed two families of catalysts. One is the noble metal catalyst, another is the nickel catalyst. This picture shows one of the test results of aromatic hydrogenation and the sulfur removal on A-set catalyst. It's a noble metal catalyst run at high temperature and high pressure. By the way, here I would like to say for nickel catalyst, the operating conditions will be much milder than this noble metal catalyst. This catalyst we can find show an excellent sulfur removal ability and very good stability. However, due to the thermodynamic equilibrium limitation, there's some aromatic and sulfur species retained in the feed. So Kimi also developed a high-performance nickel catalyst. It can be run at a low temperature and a low pressure. Here I would like to mention for the refiner, they prefer to use the low temperature because if we run at 200 degrees C or 300 degrees C, their economic performance profit will be different, very different. So we prefer to run the reaction at the lower, the better. The nickel catalyst also have the high sulfur removal ability and very high aromatic hydrogenation activity. However, this sulfur with the reaction, some sulfur deposit on the nickel catalyst and poison the active site, and the catalyst gradually deactivated. To improve the sulfur tolerance or durability will be a challenge. In this study, we made a series of nickel silicon catalyst and nickel aluminum catalyst, and we investigated their performance for aromatic hydrogenation and the sulfur desulfurization. Also, we can call it the sulfur tolerance. We found that these have some similarities, and they also show very significant differences. a very heavy diesel with the sulfur and aromatic concentration of 25% aromatic and 55 parts per million very tough sulfur species used at the feedstock. And the catalyst test were carried out in a pressurized fixed bed reactor and at 450 psi and 190 very low temperature. So this condition is very similar to the industry operating process. And the product of in the product aromatic and sulfur nitrogen cracking product were analyzed respectively. This picture shows aromatic hydrogenation performance of a nickel aluminum catalyst with the same nickel content but a different nickel surface area. We can find that all of these samples show very excellent hydrogenation activity, no aromatic leak out. However, with a different sulfur nickel surface area, the activation rate is different. Or we can say that sulfur tolerance is very different. With the nickel surface area increase, surface tolerance, sulfur tolerance increase, or the activation rate decrease. With the deactivation, we also found some sulfur leak out to the product. And again, this with the increase of nickel surface area, the sulfur uptake increase, or we can say sulfur leak out decrease. Because the hydrogenation activity always relates to the sulfur deposition on the catalyst surface. Quantitatively, we got this linear relationship between nickel surface area and sulfur tolerance. For nickel silica catalyst, the situation is very similar to nickel aluminum catalyst. Again, with the increase of nickel surface area, the sulfur tolerance increase or the activation rate decrease. And such a linear relationship can be obtained on nickel silica catalyst. However, this linear relationship is very different with the one obtained on nickel aluminum catalyst. For example, if we take these 2 points with the same nickel surface area, but their sulfur tolerance will be very different. So in summary, we can say nickel silica catalyst and nickel aluminum catalyst show different linear relationship for sulfur aromatic hydrogenation and sulfur tolerance. Also, these 2 catalysts have different interesting activity here, but this point and this point are very different. Furthermore, this picture shows compare the performance of nickel aluminum catalyst and the nickel silica catalyst with the same nickel content but a different nickel surface area. Very interesting and very importantly, we found here their initial aromatic concentration in the product is very different. On nickel aluminum catalyst, aromatic leak out very soon. However, on nickel acidic catalyst, in this cell, no aromatic in the product. That indicates that their initial hydrogenation activity or the activation behavior are different. However, after this point, after the aromatic breakthrough on nickel silica catalyst, the situation will be very completely different. The deactivation rate on nickel silica is higher than on nickel silica aluminum catalyst. This picture shows the performance of nickel aluminum catalyst and nickel silica catalyst with a very similar nickel surface area. Again, we found On nickel aluminum catalyst, the aromatic very leak out very soon. However, the aromatic breakthrough is 24 hours later than on nickel aluminum catalyst. For example, if we reach 60% aromatic in the product, their TOS is very different. Again, this point is very important. After the aromatic breakthrough, the aromatic concentration in the product increases with the TOS, and this slope stands for the activation rate. When we move this line to nickel silicon, we can find the activation rate is very similar, or as we can see, the activation rate on nickel silicon is a little bit lower than on nickel aluminum catalyst. Finally, we can give a conclusion that with the same nickel surface area, nickel silicon catalyst is more sulfur tolerance than nickel aluminum catalyst. Now, a question raised to us: why? What makes the intrinsic activity and the deactivation behavior different between nickel silicon and nickel aluminum? We consider the interaction between nickel and the spot. We also consider the acidity as well as the pore structure of the catalyst. However, based on our XPS TPR result, no evidence indicates the interaction between nickel and spot are very important in this application. For the acidity, many people believe silica has much stronger acidity than alumina, so they made a different catalytic performance. However, we don't think this is very important because both alumina and silica have very weak acidity. If acidity play a very big important role, it would result in a cracking reaction. However, in our test experiment, no cracking product was detected. So finally, we believe the pore structure plays a very important effect on the aromatic hydrogenation and the sulfur tolerance of desulfurization. Look at this picture, shows the pore distribution of nickel silicon and nickel aluminum catalyst. Obviously, we can find for nickel aluminum catalyst, pore size is much bigger than nickel aluminum catalyst, nickel silicon catalyst. Very importantly is in this area. There's a small pore in nickel silicon catalyst. This pore size might be smaller than this tough sulfur compound. As a result, this tough sulfur compound couldn't or is difficult to be diffused into this small pore. However, hydrogen is very small, can be very easily added into this small pore and dissociatively absorbed all this nickel cluster, nickel active site in this small pore. So this picture just shows for nickel silicon catalyst had a bimodal pore structure, but for nickel aluminum catalyst only single model pore structure, no micropore. Based on this investigation and the result, we like to propose such a mechanistic scenario. For the catalyst with only big pore, this aromatic and hydrogen can be absorbed this nickel active site and very easily hydrogenated to produce a saturated hydrocarbon. This is for some clean fuel, but mostly the fuel is dirty and includes some very tough sulfur. So when this tough sulfur filled with the hydrogen to the catalyst, this tough sulfur will be directly deposited the sulfur active site and the poison is the active site. So that's why we found on this catalyst the aromatic liquid gradually increased like a linear relationship because no other side can regenerate this nickel active site. If the catalyst with the micropore and the big pore, the situation will be different. For if the clean, field is clean, the situation should be same with nickel and aluminum. This aromatic very easily to be hydrogenated, become hydrocarbon and put away by the stream. If the straight faded dirty includes some top sulfur, this sulfur and the hydrogen is similar with nickel silica catalyst. This sulfur will be deposited on this nickel active site and poison this active site. However, there's a small pore in this catalyst and can stop this top sulfur compound diffusing to this small pore. Or we can say this small pore can prohibit the sulfur gain to this the small pore. And however, this hydrogen is very small, can very easily and efficiently go into this small pore and dissociatively adsorb this nickel cluster active site. This adsorbed hydrogen can very fast and very safely transport this pore, the big pore by surface diffusion or spillover. We know this spillover hydrogen is has a very high reactivity, can recover this poisoned nickel active site and produce H2S and hydrocarbon. If this hydrocarbon, all of this H2S is put away by the stream, that means the catalyst won't be active forever. However, the situation is not so good. Some H2S may diffuse combined with the nickel active site in the big pore and result in the second deactivation. Also, some H2S will diffuse back to the small pore because although this small pore can stop a big top sulfur compound going to this small pore, but couldn't stop H2S going to this small pore. So this H2S will poison the active site in small pore. Finally, when this active site poison and deactivate, this catalyst also will start to deactivate very fastly. Situation will be very similar with nickel aluminum catalyst. Finally, we give a conclusion. The high nickel surface area is crucial for hydrogenation and sulfur tolerance. Or hydrotolerance, we also can say is desulfurization. Activity and sulfur tolerance increase with the increase of nickel surface area. A linear relationship exists between nickel surface area and hydrogenation and sulfur tolerance performance. Nickel silica and nickel aluminum catalysts show significant difference for hydrogenation and sulfur tolerance. Nickel aluminum silica catalyst has a higher intrinsic activity than nickel aluminum catalyst due to pore combination effect. And shape selectivity and hydrogen spillover, or we can call surface diffusion, significantly promotes catalyst performance for deeper aromatic hydrogenation and sulfur tolerance, or we can call desulfurization. Finally, this lady and the gentleman involved in this project. Thank you for your attention. Thank you.
Yes, John.
Jisan, you reported nickel surface area per gram and pore volume per gram. Is there a density difference between the nickel silica? Are you looking at it?
Yes, this density is different actually for nickel silica catalyst. Density is lower than nickel aluminum catalyst. That means, for example, in our test, although the volume will be on specific volume space, the velocity, but the weight of the nickel silica is lighter, so less than nickel alumina. Consider this factor, nickel silica catalyst should be much more better than nickel alumina catalyst. I mean, if we put nickel silica and nickel alumina with the same weight, the shock tolerance and the hydrogenation performance should be better than nickel alumina catalyst.
And to follow up then with the lower density, you reported pore size distribution, but what about the total pore volume? It looked from your distribution curve that the nickel silica had a larger total pore volume.
For the pore volume, so essentially the pore volume on nickel alumina catalyst is bigger than on nickel silica catalyst.
The nickel alumina had a
Yeah.
larger.
Yeah, because of big pore, the bigger.
You are saying that you have advantage of nickel silica catalyst because you have a bimodal pore distribution. Did you try to use gamma alumina with bimodal pore distribution, with similar pore distribution? Like
Yeah, this is a very good idea, and actually I have been trying thinking about how to combine with the big pore material with the small pore. I mean, maybe sometimes the micro pore material comes by this combination if we can promote the performance. I'm doing this work now.
Nickel is much more active for hydrogenation than the sulfide. How can you separate the two effects?
Their mechanism is very different. For sulfide bimetallic catalysts, they operate at a high temperature and need to be sulfide by H2S. This so-called SDS mechanism. For nickel catalyst, mostly they just pick up the sulfur compound, and this sulfur. Sometimes this sulfur compound cannot be hydrogenated to become H2S, and only be absorbed all the catalyst, and it become. So that's why sometimes we only can see no sulfur and aromatic leak out from our nickel catalyst, but there's some HDS bimetallic catalyst. Second reason, the HDS reaction normally is operated at high temperature due to the thermodynamic equilibrium limitation. This because this type of sulfur normally should be some aromatic compound. Due to this limitation, this some sulfur cannot be totally hydrogenated and retained in the product.
Have you physically measured the acidity of those
No, sorry, we didn't measure the.
So you rule out that possibility because both are weak.
No, we didn't physically measure the acidity, but according to general chemistry, both silicon and alumina have a very weak acidity. Also, normally acidity should be related to the cracking reaction, but we didn't detect the cracking product. So based on this result, we conclude that acidity is not very important.
Another question. You reported sulfur leakage, and if I recall, your inlet sulfur was around 300 parts per million. And the sulfur leakage was 3 to 5 parts per million. Where's the rest of the sulfur?
Still on the catalyst.
If that's the case, then back to the acidity question. If one catalyst has more cracking or ring opening, making these sterically hindered sulfur compounds more accessible, then you may not see the effect of the cracking byproducts if they're cracked and absorbed.
Yes, if there's some cracking product, actually, one slide I indicated. Normally, this type of sulfur is very difficult to be hydrogenated. Some people believe first step, if there's some hydrogenation take place, first step should be cracking. It's multiple grain reopening reaction, then followed by the hydrogenation. But in our test condition, the temperature is very low. We don't believe that a lot of cracking reaction can take place.
Are there any more questions? If not, please help me thank Steve one more time.